So we're going to talk a little bit about concavity and also curve sketching. And so you can see a curve right here on our picture, and it is increasing from left to right, right? So it's going up the whole time, but there's a slightly different curve to it. So to the left of x equals 0, we have a graph all with increasing slopes, but is concave down. Concave down like a frown, if I were to finish that curve the way it was moving. And then on the right of x equals 0, we have concave up. Concave up like a cup would hold water, right? I could put water in there and it would sit. So that's the general idea of what concavity is. So what I'm going to introduce here is the second derivative test for concavity. So if we have a function and it's twice differentiable, and when I say twice differentiable, that just means I can take the second derivative of it. If the second derivative is positive, greater than 0, then we're going to have concave up. Concave up like a cup. Does not spill water. And if we have the second derivative less than 0, so less than 0, if f double prime is less than 0 or negative, we have concave down, and that would be like a frown. All right, and so up like a cup would hold water, down like a frown would not hold water, it would just all drip out. So we have these kind of mnemonic devices to help us remember, and that's concavity. So what we're going to be doing in this section is using the second derivative to tell us information about concavity and help us determine points of inflection. So I just mentioned this new word here, point of inflection. And a point of inflection is the spot where that concavity is going to change. So where we switch from concave up to concave down. And if we come back up here and look at this, right here at the origin at x equals 0, the concavity changed. So just like in the last section, we made tables with our first derivative. We're going to continue making those tables, but we're going to talk about both first and second derivatives. So I kind of like to make a graphic organizer here. We've got a function f of x, right? And from the function f of x, that's where we get our ordered pairs. So that is any point on the curve. Right, so then we can also talk about our first derivative, f prime of x. And f prime of x tells us if something is increasing. So positive function would be increasing. And a negative function might be decreasing. Okay, so we learned about increasing and decreasing intervals. So positive is increasing and negative is decreasing. Okay, and then the second derivative, so f double prime of x. What we have just said is that f double prime is going to tell us about concavity, and we have two options. We have positive and negative, right? So we could have a positive and a negative concavity on increasing function and a positive and a negative concavity on a decreasing function. So a positive second derivative means concave up like a cup. I'm going to sketch something down here. So this is all concave up, but where is it concave up increasing? Over here on the right side. So if it was increasing concave up, we would draw this half of that smiley face, the right half of a smiley face. And if it is concave up decreasing, we draw the left half of the smiley face, okay? Similarly, for concave down, we have concave down increasing and then decreasing. So concave down increasing is the left half of a frown. Concave down decreasing is the right half of the frown. And so when we start sketching our curves, I'm going to encourage you not to go, oh, it's concave up, it looks like this, because we're only going to have half of that concavity. It's either going to be concave up increasing or concave up decreasing. So now we're going to determine the second derivative and then also the concavity on this interval when x is from 0 to 2 pi. So even though we've talked about the first derivative and the ordered pair, graphing it, increasing and decreasing, we're just going to focus on concavity here, okay? So in order to determine concavity, we need the second derivative. So my first derivative, the derivative of 3 is 0, the derivative of sine is cosine x. My second derivative, f double prime of x, the derivative of cosine is negative sine x. So we find the second derivative, and then we're going to find our inflection values by setting the second derivative equal to 0. So 0 equals negative sine x, that's the same as 0 equals sine x. And if we ask ourselves, well, where is sine equal to 0 on our unit circle between 0 and 2 pi? We're saying, where is our y value equal to 0? And that y value is equal to 0 at 0, pi, and 2 pi. So these represent inflection values. So if we want to determine the concavity, we're going to take those values, and we have a closed interval here from 0 to 2 pi, so we don't need to look on either side. I'm going to choose pi on my x-axis. We would pick a test value on either side to test. I might test pi over 2 and 3 pi over 2. And I want to test them in the second derivative because the second derivative tells me about concavity. So f double prime of pi over 2 is what we need to test, and f double prime of 3 pi over 2. So here is my second derivative function. I'm going to plug both of those values in. F double prime of pi over 2, well, sine of pi over 2 is 1, so we end up with a negative 1 here because there's a negative in front of our function. And for the other interval, sine of 3 pi over 2 is negative 1, and negative 1 turns it positive. So where the second derivative is negative, we know the graph is concave down, and where the second derivative is positive, we know the graph is concave up. So my answer here for concave down, I'll just write CD. The graph of my original function f of x, which is 3 plus sine x, is concave down when x is from 0 to pi, and we are concave up when x is between pi and 0. So that would be the answer we're looking for here. And so you notice pi, that value that was in the center of my interval, that was where my concavity changed. So that represents a point of inflection, and we'll do more example with that in a minute. But before we do that, I'm just going to consider what the original function looked like. F of x equals 3 plus sine x. So this graph looks like a regular sine graph, and sine normally looks like that. But in this case, it's going to be shifted up 3 units. That's what that plus 3 does. So instead of starting at 0, it starts at positive 3. It goes up and then down and back up. So it's doing that between 0 and 2 pi. And right here, where the graph would be crossing, that would be my pi value. So you see it is concave down like a frown for the first half, and then the second half of my curve, it's concave up like a cup. And that inflection point in here is occurring at pi 3. And I get that output value by plugging pi into my original function. So sine of pi is 0, f of pi equals 3. Okay, so we're going to continue talking, and we have a second derivative test for local extrema. So this is a special test using the second derivative. Previously in this unit, we learned that the extreme values can be determined from the first derivative. But we can also use the second derivative to prove there's a max or a min. Okay, so using the first derivative, what we know is that if f prime is positive, then we will have increasing, and if f prime is negative, we'll have a decreasing graph. And we know that when we change from increasing to decreasing, we would have a max. If we change from decreasing to increasing, we would have a min. Okay? But what we're looking at here is a second derivative test to verify an extreme value. So if we know we have a critical number c, right? C is my critical number, and we're dealing with a second derivative that's continuous on an open interval, c exists on that interval. So if I'm looking at one of my critical numbers. So f prime of c equals 0, that's just saying I have a critical number. And if I test the critical number in the second derivative, right? Notice this is the second derivative of that critical number. If the second derivative, f double prime of that critical number, is negative, then x equals c is a max. And so you'd think negative, that should be min. But if the second derivative is negative at the critical number, we can prove that it's a max. And similarly, if that second derivative at my critical number is greater than 0, then that critical number represents a min. Okay, so plugging the critical number into the second derivative lets us prove whether or not we have a max or a min there. So if you're working a problem and it says, prove to me that you know it's a max or a min, you take the second derivative and plug that critical number where the max or min occurs into the second derivative and look to see the sign. If it's positive, you'll have a min, and if it's negative, you have a max. And of course, if it's equal to 0, the test fails. We cannot draw a conclusion. And so I still have my second derivative test up here, and I'm just going to prove to you that this is true. Okay? So what we say is if f double prime of c is less than 0, then f double prime of x is less than 0 at some point in the interval I, which contains C. Okay, so there's some other x value in there. And since f double prime of x is continuous, then we know that f prime of x is decreasing on that interval I. And since f prime of c equals 0, the sign of f prime changes from positive to negative at C. And because we have that sign change, that means we went from increasing to decreasing, there would be a max. So therefore, f has a local max at x equals c by the first derivative test. And the argument we would use for part 2 and part 3 follows in a similar fashion. I'll leave that to you to determine if you need to know that from your textbook. And just to recap what we stated, if the first derivative is 0 and the second derivative is negative, that means max. If the first derivative is 0 and the second derivative is positive, that means min.